All right, we're back to wrap up chapter 3. Last time in the last video, we stopped at this point. We had just discussed currying of arguments into a function. That is, take the inputs one at a time. And we also discussed the right associativity of the arrow operator, okay, which is basically used in the type definitions of functions to separate inputs from outputs. Okay, and that arrow operator with a minus greater sign is right associative. But when you call functions with its input arguments, like here mult xyz, we are providing the inputs one at a time, left to right, and the space which appears between these different names is the application operator, apply. Okay, from lambda calculus, it's the apply. Same thing here. Okay, and this is left associative. Okay, so mult x first, and then output of that with y, then output of that with z. All right, we got two or three more concepts here. Two important ones which Haskell uses a lot. One is that of polymorphic functions. Okay, you must have seen this in Java in other languages, but in Haskell it plays an important role, obviously. And the definition is a function is called polymorphic, or polymorphic means of many forms. Okay, it's polymorphic if its type contains one or more type variables. Okay, so what happens is that when we define functions, we want the function to operate a little bit more general, okay, not just on a specific data type, but a more generic data type. Okay, and in such situations we introduce type variables, and so these are variables very much like the variables for values, okay, like x, y, z, and so on, except that these variables denote types, okay, like an int or a char or that kind of a type, or even a function and so on, okay, function type and so on. And we use the lowercase letters a, b, c to denote these type variables, okay. So we use a, b, c as the type variable names, okay. So let's look at some examples of what a polymorphic function is, okay. Actually, quite a few of the functions we've already seen are polymorphic, even though we didn't know that they were. Okay, for example, the length function of a list. Okay, there's a function called len, L-E-N. Okay, and actually, it might be built into the prelude, but we are defining it, redefining it here. Okay, and it takes as input a list. Okay, now what it contains, what that list contains, is irrelevant, right? So when you have a list of integers, okay, length doesn't bother about whether it's an integer or not, right? It's just going to count how many items there are in the list. Okay, the type of the item is irrelevant when you're calculating the length of a list, and that's where the polymorphism comes in. Okay, so to represent the irrelevance of the type of the item in the list, we just introduce a type variable, and we say that, oh, it's a list of A. Okay, so give me a list of A as input, and I'll give you how many items there are in that list. See, that's what the length does. Okay, length doesn't bother about what type A is. A could be an int, A could be a bool, A could be a string, A could be another list of something else, A could be anything. Okay, right? If you have a list of anything, and all you have to do is find the length of that list, you don't bother about how what data type or what type that individual item is. Okay, and here's a definition which actually reflects that. Okay, here's the definition of the length function. Okay, I'm not putting the hyphen or the apostrophe here, len apostrophe. Okay, I don't want to modify the slides, but if there was a built-in length function, I'm sure there is. Okay, this might conflict with that, and typically when you have a conflict, I think the more recent version which is defined is what is used. So in that sense, when we run the len function, after defining it here, we would get the current length function is what would be used. Okay. Anyway, here's the definition of the length function. Input is a list of A. A is a data, not data type. A is a type. Okay, and the type is not relevant to us for this particular function. So the length function works as follows. If you are provided an empty list, the length must be 0. Okay, so len of left right bracket equals 0. That's a simple enough equation, right? Length of an empty list is 0. Okay, and if you have a non-empty list, and we discussed this earlier. Okay, we usually use the cons operator, the colon, which is the cons operator, and we put a variable before it and a variable after that, and put it in parentheses. And this is how you write a list with at least one item. Okay. Now in this case, what we put before the colon, you could have said x there. Okay, we could have said x here. Okay, we could say x colon xs, but because we don't care what that x is, and you can see on the right hand side, we just say it's the length of x colon xs is 1 plus length of xs. Okay, that is the rest of the list. Go find that length recursively and add 1 to it, and then you'll get the list length of the list x colon xs. Okay, and because x is not used on the right side of this equation, you can use an anonymous variable underscore. Okay, so that's a valid variable underscore. You don't give it a name. Okay, that's a variable. Okay, and this is common practice when you don't use, or when you use a variable exactly once and it's not relevant for you, you just use the underscore. Okay, and this is a reasonable definition for len, right? If it's a non-empty list, it's 1 plus the length of the tail of the list. Okay, after you drop the first item, and if it's an empty list, the length is 0. Okay, now you see that this is a polymorphic function. Okay, why? Because it's the type of this function is bracket a arrow int. Okay, and a is a type variable. Okay, and that's what a function is said to be polymorphic if you use one or more type variables in its type. Okay, so what does this give us? This gives us flexibility. Okay, lots of flexibility now. Okay, so you can apply this function to a list of integers, a list of booleans, list of strings, and list of anything you want. Okay, so and you get the correct answers. You see, so length of 1 to 3 is 3, length of false true true false is 4, length of John, Alice, Bob, Evan, Zelly is 5, and so on. Okay, if you want, we can try one more. Okay, let me try something interesting. Okay, here's length on a list of items where each item itself is a list. Okay, interesting. And obviously the answer is not 6, but the answer is 3 here. Let's see that. Okay, there you go, 3, because there are 3 items in this list. Now each of those items happens to be a list, but that is irrelevant. Okay, right? Now interesting thing would be to see what is the type of this guy. Okay, type of this. Okay, let's see let's see whether what's his name, Haskell can infer the type of this list, right? That's what we want to see. There you go. Okay, you do get an answer here. Okay, it's using a concept which we are just going to study soon. Okay, sorry about that. Maybe I should have waited a few minutes. Okay, and that's called type classes. Okay, but anyway, at the rightmost part, you can actually see the type of that list is bracket a, and the bracket means it's a list of list of, in this case it was integers, but it says that, oh, it can be integers, it can be floating points, it can be any type of numerics there. Okay, so it wrote something, this is called a type constraint. Okay, num a means a belongs to the num class. We're going to study that in a minute. Okay, so anyway, I should have waited. Okay, let's keep it here, but I should have waited on this one. Okay, so if you really want to find the type of this guy here, we had to learn the concept of a type class. Okay, anyway, in the above function, len takes as input a list of values of type a and returns an int. Type variables must begin with lowercase, and typically we use ABC. Okay, now it so happens that many of the functions defined in the standard prelude, which we have already learned, are polymorphic. Okay, so here's 5 of them. Okay, first, head, take, zip, and ID. Okay, first is built in. I don't know whether we studied this or not, but given a tuple, it returns the first item in that. Okay, so this first can be applied to a tuple of any two types, A and B, okay, and it returns a value of type A because it returns the first of these two items, okay, or of the two items in the tuple, okay. Head, which we have seen, given a list of A, it doesn't matter whether it's an integer list or a character list or a Boolean list, it'll return an A item, which will be the first item in the list, right? Remember, head was the first item. Takes an input, which is integer, and also takes the second input, which is a list of A. Now, again, is polymorphic, okay? But the first parameter to take is an integer, okay? Because that's how many you want to take out of that list, okay? But the list could have any type of elements, okay? We have some examples coming down here. We'll see those. And the answer would be a list of A, okay? So int is the input, and list A is an input. There are two inputs to take, and output is a list which looks like the second input, okay? A. Zip, I think we have seen this. If not, it's a very popular function both in Python and it's available in Haskell as well. It takes two lists and makes a list of pairs. Okay, that's what zip does. Okay, makes a list of pairs where the first item in the pair comes from the first list, and the second item in the pair comes from the second list. Okay, and um, the items are the first items are combined, the second items are combined, so on each position in the list, or yeah, that's right, in those two lists, pairs are made, okay? And if one list is bigger than the other, the rest of the pairs are ignored, okay, or rest of the values are ignored. ID is a silly function but important in theory. It just takes the input A and produces the same output of type A, okay? So here are some examples. So if I say first of 10, 20, it's a tuple or a pair, 10 and 20 integers, right? First up works on that and gives me the answer 10. I guess I need to run this. Let me, yeah. So you see that I got the output 10 here, okay? First of 10 and 20. By the way, there's another function called second, okay? SND it's called, okay? Might as well learn it right now, okay? Important functions, by the way. It'll return the 20, okay, as a second item, right? 10 and 20. First of 10, 20 is 10. Second of 10, 20 is, there's no third, fourth, fifth, by the way, okay? And actually the first and second are defined only for the pairs, okay? Now you can see that the first, because it was polymorphic, it can be applied to a list of a tuple or pair of characters and a pair of integers. Doesn't matter what type it is, you can apply it, okay? So that's why we got the A here. Similarly, head is the first item in the list, right? Head and first are similar. First applies to a pair of tuple, which is a pair. Head applies to a list. Okay, head of 1, 2, 3, 4 would be 1. Head of John, Alice, Bob, Evan, Zelly would be John. Okay, so you can see that 1 and John. Okay, and take 2 in this list. John, Alice, Bob, Evan will get you the first two items, John and Alice. Okay. And take 2 of 1, 2, 3, 4 will give me the 1, 2, okay, 1, 2. So you can see that the same function take the data type of the list which is provided in take are differing only in the type of the value, okay, but it still works, okay. So that's why it's called polymorphic, okay. It takes a parameter or a type parameter A, and that A could be anything, okay. Zip pairs produces pairs, so the 1 with the A, 2 with the B, 3 with the C, and 4 with the D, and that's how you get this output here, okay. Similarly, zip true, false, and John, Alice will combine into get to that. ID of 4 will give you 4, ID of AA will give you AA, okay. So you can see that all these functions I have illustrated with some function calls, but I can provide inputs of different types and they still work, okay. That's the idea behind polymorphic, okay. Very powerful mechanism, and when you define the function, you want to define the function as general as possible, okay. It's not interesting to define a length for a function which for a list which contains only integers, right? The same length function can work for characters and so on, so might as well make it general and introduce the variable A there, okay. There's nothing wrong with replacing A by int here, okay, nothing wrong, but you don't get the flexibility, because the length will not work on a list of characters then, okay, but you want it to work on a list of anything, okay. So that's the idea behind polymorphic functions. Okay, we are done with polymorphic functions. Okay, now in all of these examples, oh no, most of these examples uh, we had one or two variables, right? Some of them had only one variable a, some of them had two variables a and b. Okay, uh, I don't see an example with C, but there could be. But rarely you get more than two or three variables. Okay, so in most practical situations, you may have to introduce three or four variables at the most. Okay, so it doesn't get too complicated. Okay, so that is the type variables. Usually in one or two or three, you should be able to survive most of the functions you define. Okay. All right, so that completes the polymorphic functions. Now let's look at overloaded functions. Now overloaded functions are a special type of polymorphic functions. Okay, so besides being polymorphic, they must have an added feature. Okay, and and this is where we come to the classes, and which we're going to study type classes in a minute. So sort of we are introducing type classes without defining what they are. Okay, so let's look at overloaded, and you will understand with this example, one example, what's going on. Okay, a polymorphic function is called overloaded if its type, because a polymorphic function must have a type, right? Uh, and a polymorphic function is overloaded if its type variable, okay, contains one or more class constraints. Okay, so we have not yet defined what a class constraint is. We'll show an example here, but we'll go ahead and define the different classes later on. Okay, so here's an example, okay, of a overloaded function. Okay, and the function which is being defined here is the plus function. Okay, functions can be defined for the plus as well. Okay, so here's the type of the plus function. Okay, now earlier we saw the plus function for integers. Okay, so given two integers and how to add them up. Okay, but now we are generalizing it by making it polymorphic. So we are saying the type of the function is a arrow a arrow a for the plus. Okay, what does that mean? It means that it takes two inputs of type a, one a followed by another a, right, of type a. A is a type. Okay, and then it adds those two up and produces an answer of type A. Okay, so this is a two input function and one output. Okay, but instead of saying int or float or double or something like that, we are actually keeping it generic. Okay, we are saying that, oh, A, but we know that we cannot add any two things, right? It's not possible. For example, false and true. You cannot add false and true. We try to add, remember 1 plus false, we try to add. You cannot add false and true, okay? Or you cannot add two strings. You might concatenate them, but you cannot add from in the perspective of arithmetic addition, okay? Right? So this is where the class constraint comes in. We say that, okay, the type is generic, A, but we attach a constraint to that A, okay, and say that the A must be numeric, right? When you add two things, you can add only numbers, okay? So that's what this is, okay? So we do the equal greater sign to indicate that there is a class constraint to the left of it, and to the right of the equal greater than sign is the type of the function, okay? So we are introducing another feature here in the type where we can actually have a class constraint. Okay, so here we should read this as follows: the data, or not data type, but the type of plus function is a arrow a arrow a as long as a is numeric. Okay, or as long as a belongs to the num class, num class. Okay. Got it? And we will see later on that there are only certain types of num classes. Okay, some types like int and integer and double and float, those will all be elements of the num class, and we're going to define this more formally later on. Okay, so as long as a is numeric, so num is read as numeric. Okay, then the plus function can go from a to a to a. Okay, so that's really what it is. For any numeric type A, plus takes two values of type A and returns the value of type A. The type of inputs and the type of outputs of plus operator or function must come from a numeric type such as int or float, etc. Okay, so that's called. So first of all, it is polymorphic. Why? Because we are using a type variable. Okay, a arrow a arrow a. But on top of being polymorphic, it's also overloaded because we are using a type constraint or a class constraint. Okay, this is called a class constraint. Okay. numeric a, and then we put a double an equal greater sign between the class constraints and the actual type of the function. Okay. So now what will happen is that we can use the plus on 1 plus 2. We can do it on 1 plus 0 and 2 plus 0. Okay. Uh, but we cannot use it on a plus b where a is a character. Okay. So let's run this cell and see what we get. You get the 3 and 3.0. So you can see that the same plus worked on integers and on floats. And the reason is that the integers and floats are examples of numeric type class. Okay. So those two types, so int and float, belong to the numeric class. Okay, we're going to look at that in more detail very soon. Okay, so now this is if you did not define plus this way, and if you just define plus as going from integer to integer to integer, then you can do 1 plus 2, but you cannot do 1.0 plus 2.0. That would be a problem. Okay, got it? Now you might ask the question, what happens if I do 1 plus 2.4? Okay, you do get 3.4 because there is automatic conversion happening underneath. Okay, uh, just like in most other languages. Okay, so you do get, although there is a sort of a type mismatch here, 1 and 2.4, they don't belong to the same type. Okay, they must belong to the same type, a and a. Okay, but one of them is an int and one is a float, looks like it. Okay, but on numeric types, the automatic conversion takes place. This is elevated, the 1 is elevated to the float, and then the addition is done that way. Okay, all right. So I think you understood what an overloaded function is. Here's a couple of 3 others. Okay, overloaded, we just saw the plus. The multiply, same thing. Multiply has the exact same type signature. Okay, num a, which means a is numeric. Okay, and then the equal greater sign, and then the a arrow, a arrow, a. Given 2 inputs a and a, it produces an output a in the multiplication. Negate is interesting. Negate would get you the negative number. Okay, so a arrow a is negate takes one input, an integer, not integer, but any number, and returns the negative of that. Okay, and absolute, you all know, it takes a value and then it produces a positive version of that. Okay, so that type will be numeric a equal greater sign and then a arrow a, because absolute also takes only one input, just like the negate. The times and the plus take 2 input. That's why you have a arrow a there. Okay, and here are some examples of 2 times 2, 2 times 2.5, negate 2.5, and absolute minus 2.5. Okay, those are the answers. Oh, not yet. There you go. Okay, so those are the answers you get. Okay, now you see that when you write 3, the numbers, and this sort of explains this 1 and 2.4. Okay, when you take a number by itself, like the number 3, okay, and you want to know, now it looks like it's an integer because we just wrote 3 and we didn't say 3.0. Okay, but because these kind of situations can happen where we are doing arithmetic between integers and floats, numbers themselves, the literals like a 3 or a 44 or something like that, automatically are upgraded to numeric. Okay, so you can see that the type of 3 is p, where p is numeric. You see, now in this case it used p instead of abc. I think pqr is also used in addition to abc. Okay, so numbers themselves are overloaded in that they are numeric. Okay, so every number, type of number we can write, we can also say type 4.5, let's say. So you'll get, actually you got slightly different here. And we're going to learn this, all these classes. That's the topic of the next. We got fractional here. Okay, so there happens to be a class called fractional. Okay, 4.5 is fractional number. Okay, p, and under fractional you'll have the double and the float and so on. Okay, so this is the class. Okay, the num is a class, type class. We haven't learned type classes. We're going to learn that. You can see that here. Okay, but numbers themselves are overloaded by them. The literal numbers are overloaded in that they become as generic as possible by Haskell. Okay, so that you can do this cross number additions, multiplications, and so on. Okay, now we come to the last topic of this chapter, and that is type classes. Okay, we got a sort of a flavor or introduction to type classes here in the overloaded functions, but let's formally define what they are. Okay, and Haskell comes with a built-in number of type classes, and these are 1, 2, 3, 4, 5, 6, 7 we're going to study. Okay, there are a few others, and actually you can define your own type classes later on. Okay, but these 7 are important to understand, uh, and we're going to look at each one of those one at a time. Okay, and you can see that num, we have already used num and also fractional. Okay, in the above two we have seen num and fractional. Okay, so we're going to look at these type classes, 7 of these. Okay, one at a time. Okay, what is a type class? Okay, a type class is okay, let's see if I can explain it in terms of Java. I think in Java, there is a concept called interface, right? We have classes and then interfaces, okay? And a job of an interface in Java is to define certain signatures for certain operations or methods, okay? Certain methods uh, are defined in an interface, and any class can implement an interface. So you can make by implementing those methods which are specified in the interface. Okay, somewhat similar, not exactly same, but somewhat similar idea here. Okay, and that is that there are many classes. Excuse me. There are many types which we already seen integers, booleans, and floats, and this and that. There are some operations which they share some of these types, like the plus operator is shared between int and integer and float and double and so on, and fraction, not fractional, but those 4 things we saw before, right? Int, integer, double, and float. Those 4 data types share the plus operator. Okay, right? Because you can add any of those 2 things, right? Because those 4 types implement the plus operator, that's why they all belong to the num class. Okay, and so on. So these are classes, type classes, which we're going to look at definitions, and each of the definitions includes certain operators which must be implemented. And if any other type implements those operators, then those types become members of this class. Okay, so that's the idea. So let's look at these one at a time. The concept becomes clear as we look at the examples. Okay, so the first class and the simplest type class. So we are discussing type classes. Okay, the simplest type class one can create is called the EQ. Okay, and these are starts with uppercase, and then EQ is the exact spelling there. Okay, and what this class does is that it says that this class contains types whose values can be compared for equality and inequality. Okay, using the following 2 methods. Okay, double equals and not equal. So by the way, this is how you do not equal to, forward slash and equal to in Haskell. Okay, so forget about the exclamation equal to and whatever else we have not equal to. Okay, so in Haskell it's very unusual. The not equal to is forward slash equal to. Okay, so these 2 operations which have the corresponding types a arrow bool, same thing for this one too. Okay, so these 2 operations written this way, double equal to and this way. Now when you do it as infix, you provide the parentheses, but when we use it in examples, you'll see that we don't need to provide the parentheses, especially if you use it infix. If you use it prefix, then you have to use parentheses. Okay, so this is obvious. It says that double equal to means you're comparing 2 values for equality, and which means that you must have 2 inputs, and those 2 inputs could be any type, a and a. Okay, any type. So they could be integers, they could be characters, they could be strings, they could be anything, as long as there's a you can implement the comparison and return a true false value. uh, it should all those types will become automatically EQ member of the EQ class. Okay, so this is like the operator or the method in Java in the interface. Okay, it says that, oh, as long as you implement these 2, then if you are a type and you implement these 2, you have membership in my class, EQ class. Okay, so they become, and obviously the bool, char, string, int, integer, float, double. Remember, these are the 7 basic types. They're all examples of EQ. Okay, they all belong to the EQ class, and we refer to it as instances of the EQ class. Okay, these types, these 7 basic types are all instances. Why? Because we can compare 2 booleans, okay, false and true, whether they're equal or not. Okay, right? Same thing, given 2 characters, we can check whether they're the same or not. Given us 2 strings, we can check whether they're the same or not. And same with these numeric types, right? So we should be able to compare all of these 7 values with itself. Okay, 2 values in the same type, we should be able to compare for equality or inequality. Okay. Now, list and tuple, which are a little bit more generic types, also belong in the equality as long as their components, lists and tuples contain components, right? List contains only one component, but tuple can contain many components of different types. As long as those individual types which are used in the definition of lists and tuples, they belong to EQ class, the list also and the tuple also will belong to the EQ class. Okay, but if the components do not belong to the EQ class, then the list and tuple also will not belong to the tuple EQ class. Okay. Now, it's interesting that the function types are not in the EQ class because it's really not possible to compare 2 functions for equality. Okay, it's not possible. Okay, so that's why they do not belong. Okay, so EQ is almost anything can be compared, right? All these are compared, but lists and tuples also can be compared if the components are comparable. Okay, so this is somewhat like comparable. I think so. In Java, there's an interface called comparable. Okay. Okay, here's some examples. False equals false, A equals B, ABC string equals ABC, the list 1, 2 not equal to list 1, 2, 3, and then the tuple A20 equals tuple A30. Now these are all comparisons you can make, and when I run this cell, I get true falses here. You can again ignore this suggestion, okay? But here the answer is true, false, true, true, false. First is true, the second is false, the third is true, fourth is true, and the fifth is false. You can see that it's quite obvious. Okay, so you can compare 2 values with the double equal to or the not equal to like this for most types. Okay, not all the types. You might some types later on in chapter 6 and 7 we are going to define our own types, and some of those types may not be comparable and so on. Okay, but certainly in the basic types you should know that they're all comparables. Okay. Okay, and that's all that is, okay, in the EQ class. Okay, so we have learned the EQ class. And so the main thing to remember is these 2 operations of comparing for equality and comparing for inequality. Okay, now let's look at the ORD class. This is the next one. Okay, ORD stands for ordinal. Okay, this class contains types that are instances of EQ. So to be in ORD, you must be in EQ. Okay, so you must be in EQ. A type can be in ORD only if it is in EQ, because that's what it says. Are instances of EQ that are totally ordered. Okay, and as such can be compared with these 6 operations. Okay, so if you can if a type is there and it belongs to the EQ class for all practical purposes, every type is in the EQ class. Okay, not all, but almost all. Okay, and any of those types can be in the ORD class if they support these 6 operations. Okay, less than, equal to, greater than, equal to. Remember those 4 other comparisons besides those 2. There are 6 normal comparisons we make. Okay, so and each of these has the same type, a bool. Okay, 2 inputs and comparison. Okay, and also for the if they're totally ordered, you can find a minimum and a maximum element, right? Totally ordered means there's a linear chain of ordering. The smallest, the next smallest, excuse me, yeah, that's right, smallest, next smallest, next smallest, and then all the way up to the highest. Okay, if you can linearly order all the items in the type, then it's called totally ordered. Okay, and those types we can do these 6 comparisons on any 2 items. Okay, the min and max will compare 2 items and tell you which one is bigger and which is smaller. Okay, a min of 2 and max of 2. Okay, all right, so that's the odd type. Now an odd type must be an element of EQ type as well. Okay, but odd class. Okay, now this is a class. Okay, now any type such as bool, char, string, int, integer, float, double. Now all these 6 or 7 of these are automatically elements of odd as well, because you can do these 6 operations on the on these 6 or these 7 types. Okay, and same goes with the list and the tuple. As long as the components of the list and the tuples are instances of odd. Okay, So there you go. Okay, so we have learned two type classes. Okay, EQ and ORD. And for all practical purposes, all of the basic types and the list and the tuple belong in these two type classes. Okay, and some examples: false, less than true, you get true. Okay, let me run this. False, less than true is true. Min of A and B is A. Min means the smaller of the two. Elegant, less than elephant. Okay, is true. Why? Because this is a lexicographic comparison. Okay, G comes before P. That's why. Okay, 1 to 3 less than 1 2 is false. Okay, now this again is lexicographic. 1 is not less than 1, and that's why. Okay, so a list and a string like that, lexicographic. Okay, tuples again lexicographic. Okay, A less than B, yes. Then 2 less than 1, no. Oh, actually it stops at A less than B. Okay, as soon as you get the first comparison true, you can stop. So that's why you get true here. And A2, A1 is false because A is not less than A. Okay, that's why. Okay, but suppose you said less than equal to here, then also it will be false. This last one will still be false. Why? Because A is less than equal to A, but 2 is not less than equal to 1. Okay, so I think that would have been a better example there. Okay. All right, so we learned EQ and we learned ORD and we looked at some examples. Okay, now comes show and read. Okay, these are two interesting ones. These are the same as actually the show is the same as the toString. Remember in Python we had the underscore underscore str underscore underscore, and in Java we had toString. Same thing here. Okay, the show, what it does is that this class, so it's again a class type class show, whose values can be converted into strings of characters. Okay, so this is the only operator. Okay, so this is a function which must be implemented for a type to belong in this class. Okay, show. So if you do build a string version of the type value, okay, then it can belong to the show class. Okay, so the data type is a arrow string. Okay, and this is useful to print things out, right? So the toString. So if you want to print a value in a particular type, if you don't have the show, you cannot print it. Okay, so you want to show this to the screen, okay, or to the terminal or whatever. Okay. Now by default, bool, char, those 7 basic ones, and also the list and the tuple, as long as the individual components are also instances of show, these are all showable. Okay, so you can see that show false, show A. When I do that, you can actually see the string version of those here. When it says show false, I get false as a string. When it says show A, I get A as a string. You can see that there's an extra double quotes. When I say 1 2 3, this is a number 1 2 3, 123. Okay, and that's been shown as a string 1 2 3. So you're converting each of these values into a string. Okay, and this basic and the list and tuples are automatically built in to be members of show. Okay, all right. So show is the toString method. Now read is just the dual, or the not the opposite but the dual of show. Okay, so show converts a value to a string. Read converts a string to a value. So you can see the type signature here. It converts a string to a value. Okay, now this is useful when you read from an input. Okay, and automatically convert the input string to a number or a double or whatever it is. Okay, so that's what the read is. Okay, and read would work as follows. Okay, so again by default all these 7 data types, the basic types, are examples of instances of read class, and also list and tuple as long as the components are instances of read class. Okay, so you can actually convert strings which contain certain values of a certain type into the value of a certain type. Okay, so for example, when you say read and give the string which contains false, okay, then this one will be converted into you can see that when I run this cell, I get the false boolean. Okay, so actually this gets converted into a boolean automatically. Now I think in some of these, this colon bool is the colon type is necessary. Not not all of them, but most of them it's necessary, the type, because otherwise when you're reading false, it could just be a regular string as well. You may not be reading boolean, right? False may appear in the middle of a sentence as a string. Okay, so that's why, because of that ambiguity, when you use the read function, you have to indicate to the Haskell interpreter what type of value you want to read into. Okay, so if you want to read this into a string, you can. If you want to, then it'll read it into a string. Okay, but in this case, I want to read into a bool, so I do that. If I want to read the string 1 to 3, I could read it into an integer if I want. Okay, and when I do that, I get, you can see that in the printout, I get the 1 to 3 automatic conversion from the string 1 to 3 to the number 1 to 3, the integer 1 to 3. Okay, and same thing here for the character, and here list as well. So I can take a list of numbers as a string and convert it into a list of integers. You see. So this is the backward conversion. Normally you have a list of integers and do a toString or show, and then you get a string which contains that, like here. Okay. So this is the backward. Okay, and same thing you can do on the tuple. Okay. Now in the last one, the type is not necessary. Okay, almost all of the others type is necessary, but the last one is not necessary, and mainly because of the type inference of Haskell. Okay, let's see why. Okay, so we're saying that read false. Now if you just said read false, then the type is necessary, the bool is necessary. Okay, because Haskell has no way of determining that, oh, the user wants a boolean when he reads false. Okay, but because the user specified not in front of it, Haskell can infer that this whole type must be boolean. Why? Because the signature of not was bool arrow bool. So from that it remembers, oh, not is bool arrow bool, and this so this guy must be bool because this is the input bool. Okay, which means that the reads output must be bool, which means that, oh, I must read this into a bool. You can see that there's a lot of logical inference happening inside Haskell with the same type inference which I talked about right in the beginning of the last lecture. Okay, and that's why this specifying bool is not necessary. But if you do specify, it's fine. Okay, Haskell will double check. Okay, it won't trust you. It'll double check, and it'll make sure that what you specified is what it figured out. Okay. Anyway, now you can see that read false and not of that comes out as true as a boolean value here. Okay. So that's the show and the read. Okay, so we are done EQ and ORD. EQ and ORD are related. Okay, and every ORD must be EQ. Okay, remember. So EQ, only the two comparisons, equal to and not equal to. In the ORD, we have 6 more comparisons. The 4 other comparisons of less than, greater than, less than, equal to, greater than, equal to, and also the min and the max. Okay, so those are the 2. Then the show and the read are useful. Okay, for converting to string a value, and also converting a string into a value. Okay, and then we talk about num, which we have already introduced before. This class contains types whose values are numeric, and as such can be processed with these 6 operations. Okay, so these are the 6 operations which defines a type to be numeric. Okay, and those are plus, minus, multiply. Okay, you notice that the div is not there. Okay, we're going to come to the divide separately. Okay, plus, minus, and multiply, and negate is the same as the unary minus. Okay, but in Haskell it's written negate. Okay, and absolute we have seen, and sign num we have not seen, but that just returns a sign of a number. Okay, whether it is positive or negative. Okay, so it will be 1 plus or minus 1 output. Okay, input can be any number, output will be plus 1 or minus 1. Plus 1 if it is positive, minus 1 if it's negative. Okay, you can see some examples here. And here the basic types integer, float, and double are all instances of num because they support these 6 operations. Okay, these 4. Okay, now we'll come to divide. Now you're still worried about divide, right? I'm also worried about divide, but we'll come to that in a minute. Okay, so plus, minus, multiply, negate is the negative. Okay, absolute we know, and sign num is the sign of the number. Okay, so 1 plus 2 should give us 3. 1.0 plus 2.0 should give us 3. Negate of 3 should give us minus 3.0. Absolute of parenthesis minus 3 should give us minus 3. Now you'll notice that when you do a negative number like minus 3, you have to give parentheses. If you don't give the parentheses, there is a one of those precedence rules comes in, and the space operator has the highest apply. So abs will be applied to minus or something like that. So that's why this parenthesis is necessary when you put negative numbers. It's a little awkward, odd feature in Haskell, but you're supposed to give parenthesis on negative numbers. Okay, sign num of minus 3 will be minus 1 because it's a negative number. Okay, So these 6 operations, negate, absolute, and sign of a number, plus the 3 arithmetic operations, plus, minus, multiply. Okay, those define what a numeric class is. Okay, now let's come to the divide. Okay, now there are 2 types of divide. Okay, one is obviously the integer division, and there's a fractional division. Okay, so let's focus on the integer division now. Okay, so any type which is in the numeric class can also be a member of the integral class if it supports these 2 operators. Okay, the div and the mod. Okay, these are the integer division and remainder. Okay, and the signature obviously is a arrow a arrow a arrow a for these 2. Okay, and this is how you do div. Okay, it's not the forward slash. Okay, so if you use it infix, you use a tick mark before and after that. Okay, so and this is a peculiar notation in Haskell, is that a function can be done infix if it operates on 2 inputs like that, and when you use that function infix, you have to put this tick mark, which is the symbol which is to the left of 1 but with the shift, okay, on the keyboard. So 7 div 2 would give us 3. Okay, it's the integer division. 7 mod 2 will give us 1. It's the mod. Now the same div and mod can be done with the prefix notation, and now you don't have to give that tick mark. Okay, so you can just say div 7 2, that'll give the 3. Mod 7 2 will give it the 1. Okay, but if you do want to use it infix, then you have to go the tick mark there. Okay, so the integral class supports the integer division and integer remainder modulus function. Okay, so obviously I think it's not mentioned here, but int and integer would obviously become members of the integral. Okay, floats and doubles would not, because I think these 2 operations technically we are not supposed to use with floats. Okay, okay, now we come to the fractional, which is the last of the classes. Okay, so integral is mainly to handle the integer division and the remainder. Okay, fractional is for the divide. Okay, so remember the divide was left out. Okay, so this class contains types that are instances of the numeric class, just like the integral. These also must be from the numeric class, but in addition, whose values are non-integral. Okay, and as such support fractional division and fractional reciprocation. Okay, so slash, and we use the normal symbols for the fractional division, slash. Okay, a, and reciprocation is 1 over. Okay, a arrow a, so this will just do 1 over the input. Okay, so 7.0 divided by 2 would give you 3.5. Okay, because the float and the double are numerics which are also fractionals. Okay, and reciprocation of 2.0 will give you 1 over 2.0, which is 0.5. Okay, and that completes this particular chapter in all. Okay, and it's important. Let's sort of summarize these 6 classes here. EQ are the 2 operations, equals and not equal to. Okay, OR is the comparison operators, the remaining ones, including the min and the max, and then show and the read are converting to string, and vice versa. Okay, and the numeric is obvious. It supports the plus, minus, multiply, and also the sign, sign num, and absolute, and negate. Okay, and the integral would be the mod and the div, and the fractional would be the divide, the actual divide, okay, of 2 numbers, slash, and the reciprocation, which is 1 over that. I wonder why a name was given to it. Okay, you can always say 1 over that, right? So just as a feature of Haskell, you can do reciprocation with a function. Okay, all right, I think we have finished chapter 3. Let me stop the video, and we'll come back for chapter 4 in the next video. Okay.